I'm going to go over Lagrange's theorem and the proof for Lagrange's theorem. First of all, Lagrange's theorem says if G is a finite group and H is a subgroup of G, then the order of H, in other words, the number of elements in H, actually divides the number of elements of G. So if you think about what that means you can't have some weird, like for example, if you have a 10-element group, you're not going to have some 7-element subgroup in there. All the subgroups have to divide, their orders have to divide the order of G. Okay, now in order to prove Lagrange's theorem, you need two important lemmas. So lemma 1 would say for all for all elements A in G, HA, so the coset HA, is actually the same as the equivalence class of A mod H. So in other words, all the X in G where A in is congruent to X mod H. We have to prove that first. Alright, so then once we do that, we're going to prove lemma 2, which says that there is a one-to-one correspondence between any two right cosets of H and G. Once you have those two pieces, Lagrange's theorem is actually very easy to prove. Alright, so let's go ahead and prove lemma 1. Okay, so again, lemma 1 says for all A and G, HA, the coset HA, is the same as the equivalence class A is congruent to X mod H. All other things are equivalent to A mod H. Okay, so I'm going to prove this. And so, first of all, let's let this bracket A mean that set all the things that are equivalent to A mod H. That's just for notation purposes. Okay, so now what I'm trying to show is two sets are equal. How do you do that? So first you have to show, so we must show that the coset is a subset of the equivalence class, and we have to show that the equivalence class is a subset of the coset. And then, in that case, so we should put the or equal to. If we show those two things, then they're equal. Okay, so for a little h in H, so we're starting off with picking out an element of my coset. So the elements of the coset look like HAs, right? So the little HAs are the elements of this coset. So if I take an element of my coset and I take its inverse and multiply it by A, if the result is in H, then that is in this set by definition, because what does it mean to be congruent to X mod H? This means that AX inverse is in H. Okay, that's the definition. So here, if HA inverse times A is in H, then we've shown it. Okay. Well, that's actually not very bad, because I can distribute the inverse like this. Remember, you flip your properties, and that results in H inverse, and that has to be an element of H, since, why is that? Since H is a subgroup, and the subgroup is closed. Okay, so it'll be closed under inverses. That means that HA is congruent to A mod H. In other words, HA is in your congruence class of A. Thus, there's the first part. HA is a subset of my equivalence class. Okay, so there's the first part. Okay, now what we need to do is let's pick something in the equivalence class and show that it's part of the coset. So let's suppose, let's just pick an X, I guess, in the equivalence class. Alright, so that means that A times X inverse is an element of H, right? That's the definition of modulus. So now if you take the inverse of that, you end up with X A inverse, and that is in H as well. Now why would we do that? That's a little confusing. What this means then is that that means there exists an H in the subgroup such that X A inverse equals H. Right? Why do I know that? Because X A inverse is in H, so we're just defining it, okay? So now, when you multiply both sides, let's multiply by A on the right. We get X A inverse times A equals H times A, which implies X equals HA. So wait a minute, that means X is in the coset HA. Okay, so there we have it. Thus, HA is equal to the equivalence class of A, because we've shown from both sides, right? Alright, so there's a proof of Lemma 1. And I hope that makes sense. Alright, so now let's go ahead and prove Lemma 2. Okay, now, so remember, Lemma 2 says that there's a one-to-one correspondence between any two right cosets in G. Alright, so how do we do this? Well, from Lemma 1, cosets are equivalence classes. And in a common algebra text, you'll have proven by this point in the course that equivalence classes form a decomposition of G. Okay, so these classes decompose G into sets. So what does that mean? That means that any two right cosets in G are either identical or have an empty intersection. Okay, we could write this symbolically as thus G equals a disjoint union, that's how you write it, U with a little dot in it, of HA going over all cosets in the group, okay? So it breaks them up to this disjoint union. Now, what we have to know then is that there's a one-to-one correspondence, right? So we know that if you take two cosets, they can't have anything in common unless they are the same thing. Okay, but are they the same cardinality? They have the same number of elements in it. We're going to exhibit our one-to-one mapping in this way. So for little HA, which is an element of the coset HA, okay, and remember, what is the coset of HA? It's the set of all products, all the H's in your subgroup times the element A, right? So we're picking a particular H here. We're going to associate it with H of B and the coset HB. Alright, so remember, this is for the particular H. So we can generate H of A, capital H of A, by multiplying A by all the little h's. In the same way, we can get capital H of B by multiplying B by all the little h's. And so we consider HA, this particular instance of HA, associated with this particular instance of HB. Alright, now I'm claiming that this is the mapping we need. Okay, so it is definitely onto, because I can multiply all the h's times b, and for each h I can find an HA. Now, is it one-to-one? Yes. Why? Because, let's say, so for if we took the elements h1b and that equals h2b, well, that implies, since h1 and h2 are in H, that the things that they came from will also be equal. So H1 equals H2. So if I have two images that are different, or I'm sorry, if I have two images that are the same, H1b and H2b, then they actually came from the same pre-image, H1a and H2b. So now, H1a and H2a. So now what we've shown is that the mapping from one coset to the next can be done in this way, and that it's a one-to-one mapping. And that's what we're trying to show. And the reason that we needed Lemma 1 is because it allows us to use the fact that equivalence classes decompose G into sets. Okay, now that we've shown Lemma 2, Lagrange's theorem is pretty straightforward. So let's go and get into Lagrange's theorem then. Okay, so now we're finally to Lagrange's theorem, which again says if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. Okay, so to prove this, we've already done the hard work with Lemmas 1 and Lemma 2. Okay, so let's let G be finite. By Lemma 2, the size, or the order, we should say, or the cardinality, however you want to write that, we can denote it like this, but the way we've done it in our statement is the order of H is the same as the order of any coset. Okay, they're all the same cardinality. And we also know, or we can suppose, let's suppose that G has some number, let's say k, distinct right cosets. Alright, so we already know from Lemma 1 that the cosets make up every element in the group, and they each only go into one coset. We also know from lemma 2 that they're all the same cardinality. So by lemma 1 and lemma 2, any two distinct right cosets, let's call them HA and HB, we know have no intersection and they have the same order. Okay? Thus, the order of G will be the order of H plus the order of HA plus the order of HB plus, and keep going out to order of HD, let's say. And here we have, how many of these do we have? We have K of these, and they all have the same cardinality. This is K order of H. Look, by definition, we see that the order of H divides the order of G, which is exactly what we're trying to show. Alright, now the way to visualize this is it's like you have a big box of toys, okay, but then you have to put them in the bins. So you put some of your stuff in this bin here, and now you've determined that each bin needs to be the same size, and nothing can go in more than one bin. And that's exactly how these group structures work. You have HB, HC, and so on. They're all the same size, and they all have the same order, and they make up the group completely. So of course then, the number of things in this box has to be able to divide the number of things total. And that's what we ended up with right here. So there's the end of your proof. I hope this makes sense. If you have any questions, please let me know, and thanks for watching.